So previously we discussed the unlimited population growth model, and now we'll move on and we'll introduce the limited population growth model. So we have the same setup, that is, we have some population whose size is determined by the function p that tells us how big the population is at time t. And when there is no constraint, your population grows and grows and grows, and there's nothing really to stop it. So, and if it grows at the rate proportional to the size of the population, then we have the unlimited population growth, which we found to be this. Where R was the growth rate and P of P0 was the initial population. Now, when there is a constraint, and what exactly do we mean by a constraint? Well, assume that the environment can only sustain a certain size of the population. So no more than 10 billion people can live on planet Earth, for example. So this upper boundary, which we can, let's say, set at L, so L stands for the limit, and it's called the limiting or carrying capacity. So what happens if you look at a function that grows but has the limiting capacity? So clearly it cannot grow through that limiting capacity, right? That would be a violation of the condition. So what's going to happen? Well, naturally we would expect the population to grow rapidly at the beginning when the limiting capacity has no effect. But then as you approach to the limiting capacity, the growth rate should slow down, and then you should be approaching the limiting capacity in the limit, but if you reach it, then you'll stay there, but it is possible that you will never reach that capacity. So the question is, what will be a model or a function that models such behavior? And we're going to do a similar development as before. That is, we're going to first create some sort of mathematical statement in the form of a differential equation that describes the behavior of the system, and that's the first task. So given this function that represents the population and it is unknown, so the question is, can we say something about the rate of growth? And if we can, then we can set up the differential equation. So turns out that the following equation does describe the behavior that we verbally described earlier. This equation does the same, does a great job at describing the same behavior mathematically. So again, we're saying that the rate of growth is proportional to the population and this difference between 1 and P over L. So what exactly does 1 minus P over L represent? Well, when P is near 0, what do we have? Well, 1 minus P over L is equal to 1. And around p equals 0, what do we have? We have the rate of change being very similar to the one without any constraints, which is kind of what we described earlier. So when you are far away from the limiting capacity, when you are around here, you are really not concerned about the capacity, so your behavior should be very similar to the behavior of a unlimited growth. And on the other hand, when population approaches the limiting capacity, what's going to happen here? I guess I shouldn't be putting the equal sign. I'll just draw like the approximately equal. And when p approaches to L, then 1 minus p over L approaches to 0. And then dp dt will be approximately equal to 0, because when one of the factors is 0, the whole product is also 0. And dp dt equal to 0 means what? That means the population isn't growing, which corresponds to having a horizontal tangent line, which is kind of what we're observing here near the carrying capacity. So does this equation describe the behavior well? It seems like it. So what's the next step? Well, the next step is to try and solve this differential equation, but we're going to solve it as an initial value problem. So let's also introduce P0, which will represent the population size at time 0. So we have the following equation to solve. And again, this is a differential equation, and in order for us to solve it, we have to classify it first. And what type of equation this is, we know a few, and it appears that this is a separable differential equation, and that means we can solve it by separating the variables p and t. We're going to treat p as a variable now, so on the left side we're going to have dp, and let me write it like this. So we're going to have dp, and we're going to have p1 minus p over L here, and on the right side we're going to have just dt with the coefficient k. And here I'm going to multiply the numerator and the denominator of the fraction on the left by L. So I'm going to throw L in there, and then I'm going to distribute L over this subtraction. So we're going to have L minus P. And now, after I add the integral, it all makes sense. And we continue solving it by integrating the left and the right hand side. So on the left we have a fraction. So if you recall the method of for integrating rational functions, one of them, like let's say if you had to integrate a function like this, let me put x instead of p, just so we are more familiar with x's, I guess. How would you integrate this function? Well, we would do the partial fraction decomposition, and believe it or not, but this fraction decomposes into this exactly. So the integral will be ln of absolute value of x minus ln of absolute value of x minus L plus c. So that means the left hand side, the integral now becomes now we're just going to write p instead of x, so ln of p minus ln of p minus L we're gonna put C on the right hand side. And on the right side we have kt plus C. And we know this is not our last constant of integration, so we're just going to put C1 over here, and we're going to continue solving this equation. Since P represents the population, it is fair to assume that P is greater than 0. And at the same time, we know we have a carrying capacity, so P must be between 0 and L. So what does that mean? That means the absolute value of P must be the same as P, because P is positive, but absolute value of P minus L, because P is less than L, P minus L will be the opposite of L minus P, but L minus P is positive. So the absolute value of P minus L is exactly L minus P. So this is how we get rid of all the absolute values. And we're also going to use the law of exponents, and we're going to rewrite ln of difference of logs as the log of the quotient. So what we have here now is ln of P over L minus P, and on the right side we have kt plus C1. Next we're going to exponentiate both sides, so we have P over L minus P on the left, and on the right we have e to the kt plus C1. But if we let e to the power C1 be equal to C2, and it could be our last constant, then I'll just get rid of the index. Yes, it is. So let's just let e to the power C1 be equal to C. Then it seems like we have a solution, but it is in implicit form. In implicit means we don't have P isolated yet. So if we want to isolate P, we need to recall like this simple algebraic method of isolating a variable when it is wrapped in a rational expression. So how do we isolate x in here? Well, we multiply both sides by 6 minus x, distribute, add 2x to both sides, and then divide by 3. Well, exactly the same way we're going to isolate x when we have something like this. And here we can put something else, like it doesn't matter what you have here. We will multiply both sides by the denominator, then we will distribute, then we will add this many x to both sides, and then we would factor out x, and then we would isolate x by dividing both sides by 1 plus whatever that is. So what does that mean? That means when we have P over L minus P here, P over L minus P equals C e to the power kt, we're going to multiply both sides by L minus P. We're going to distribute. We're going to add. And we're going to factor out P. and we're going to divide. And now we have a solution to the differential equation in explicit form. So we have our limiting capacity L times some C e to the kt, all that divided by 1 plus C e to the power kt. And now remember, we have it as an initial value problem, so we want to rewrite it as simple as possible before we start solving for C. So let's divide everything by C e to the kt, like so, the numerator and the denominator. So we're gonna have L over, and here we're gonna have 1 over C e to the power negative kt plus 1. So one may disagree that this is a simpler form. However, we only have k and t and c appearing once in this expression in comparison to not both, but c, k, and t appearing twice in this expression. So we do like this one more. Now we need to solve for C. So to solve for C, we're going to, so to find C, we just start a new slide. To find C, we're going to use the initial condition. So when we plug in 0, we get P0. And on the right side, when we plug in 0, what do we get? We get L over 1 over C e to the power negative K0 plus 1. And e to the power 0 is just 1. So what we have here is, let's summarize. So we have 1 over C plus 1 is equal to L over P. And 1 over C is equal to L over P minus 1. And if we look back here, we actually don't need to find C. If we just find 1 over C, that will be sufficient, which we did. So to plug everything back in, what do we have? We have a function P of t, in which we have L in the numerator. In the denominator, we have 1 over C, but we can express it like this, times e to the power negative kt, and we also have plus 1. So one last thing I'm going to do here is I'm going to get rid of the fraction within a fraction, so I'm going to multiply everything by p. So, and this should be p0 right here, otherwise it makes no sense. And we multiply everything by p0, so in the numerator we have L p0. In the denominator we now have L minus p0 e to the negative kt plus p0. Remember, we multiply by p0. And this is what we call the limited growth model, or the logistic equation. Alternatively, it can be written like this. So just like we multiply everything by p0, we can also multiply everything by e to the power kt, and then we have something like this. So I personally prefer this format because you only have to plug in t into one place, while here you have to plug in t in 2 places. So to summarize, what do we have? We started off with the following differential equation. And just like in the unlimited growth model, let's just use R instead of K. In algebra, K is good for coefficient of proportionality, but here R will represent the rate of growth. So we started with this differential equation, which we can call the logistic model. And it was an initial value problem. And we solved it. So we found the function p of t, and the solution is, again, I'll write it in both ways. So it's LP0 over L minus P0. Again, this is R. Alternatively, we can have that extra e to the RT here, and here. And this is what we call the logistic equation. And in this logistic equation, L is what we call the carrying capacity or limiting capacity. P0 is the initial population. R is the growth rate. So again, the growth rate tells us how fast the population grows if there was no limiting capacity. So this is what we call the limited growth model. It's synonymous to logistic equation. And let's do an example. So if we have the following formula, let's identify all the ingredients in this formula. I'm sorry, not the formula, but the actual differential equation. So let's identify all the components and then write the answer. So based on the way the equation is written, the limiting capacity will be 350,500, and the rate of growth will be 0.74. So we don't have to resolve it again. We can just write the solution using this formula. So just pick which of these two expressions you would like to use, and I'm just gonna pick this one, the one on the left, and I'm gonna apply it. So the solution to this problem will look like this. We're gonna have the limiting capacity multiplied by the initial population, and all that divided by limiting capacity minus the initial condition. So what we're noticing here is actually the initial population here was bigger than the limiting capacity. So, for example, if somehow suddenly we had 20 billion people on Earth, while Earth can only sustain 10 billion, so what would happen? Your population has to decline, right? And so let's just continue plugging it in. We have e to the power negative RT, so it's going to be negative 0.74 T, and we're going to add the P0, which is 1. So again, the idea is that once you identified all the components, you don't have to solve the equation by hand. You can just use this, what we call logistic equation formula.